All right. So what's this class all about? Thermodynamics. The study of energy. The study of energy, because energy can be in different forms, and you can transform the energy between forms. As a clever mechanical engineer, we create devices that do that. And then we can analyze the performance of those devices from energy concepts. So it's all about energy, the conservation of energy, the transformation of energy between forms, and that transformation's limited in many cases. We're going to talk about life-affecting applications first, then we have a lot of topics, a lot to go through today. Why life-affecting applications first? To motivate you, to show you that this class is applicable. But you'll never respond to an ad where a company wants to hire a thermodynamicist. They're very few and far between. This is one of those foundational topics in mechanical engineering. To do good work in other areas, you have to master and apply the concepts of energy and thermodynamics. So power plant, this is a picture of a 585 megawatt electric. That's the thermal, not the thermal output, the electric output from a CPS plant. It's located at Calaveras Lake. Maybe you went down there before. It's a Spruce power plant, and it's owned and operated by City Public Service, now just CPS Energy. And they burn coal to make electricity. How does it work? You have burning a fuel to boil water, to blow it through a steam turbine. The steam turbine's connected to a shaft to electric generator. Rotating magnetic fields create electric current. Distribution, voltage transformers, power lines. Eventually it comes all the way out into this building right here. This power, electric power used in the lights and the equipment in this room comes from CPS. Okay. They also have nuclear power. You may have heard of nuclear power plants. Here is a containment structure. Here we have a reactor vessel with an illustration of rods, fuel rods, and control rods to control the fissioning. Controlled nuclear fission. When it's uncontrolled, it's a bomb. But when it's controlled, it's a power plant. Okay, fissioning of uranium-235, breaking apart that big heavy nucleus, releasing a lot of thermal energy. It's used to go to a steam generator to boil water, which comes outside of the containment, so a secondary loop passed through a steam turbine, connected to generator to make electric current and sell it off to the grid. You then cool it. You either have a tall cooling tower, or you just put it into a lake. Most of our lakes are done. In Texas, we build power plants next to lakes to reject the heat. All right. So controlled nuclear fission, but it's the same thing as burning coal. You boil water. Where do we have nuclear power plants in the state of Texas? Well, here is Houston. Okay, here's I-10 running to San Antonio. There's Gonzales, Victoria. And right down here, we have the South Texas project near Bay City. Bay City, anybody from around Bay City? A lot of jobs down there in the nuclear power plant. I don't know how many thousand employees they have, but they've hired UTSA mechanical engineers as well as electrical engineers that are productive, having fulfilling careers down at that site. They have 2 nuclear reactors. Both are almost 1,300 megawatt. They will be running probably throughout your lifetime. I know they continue to go in for license extensions. I think they were originally built with a 50-year life, but they're probably stretching it out to 100, 150. So they'll be there for a while. So there are 2 very big plants. Notice that there's a little bit of blue right in here that's for water. What's right there? That's a big lake. They made that lake. It's like a 7,000-acre lake to supply cooling. They, before natural gas became cheap, they were already had submitted 2 additional applications to build 2 additional reactors at that one site. So they have 2 reactors now operating, been operating since early 80s, mid 80s, I can't remember the year. And then they were going to build 2 more at that site because they have plenty of capacity in the lake in the cooling water. Okay, they designed the civil structures to accommodate it. So Who owns these two reactors? City of San Antonio owns 40%. Last year, 30% of the electricity used here in this building was from those two reactors, that power plant. 30% of what you used as a citizen of San Antonio came from nuclear power. Whereas the other 16% is owned by Austin, 44% by NRG, which bought out Reliant, which bought out HLP, Houston Lighting and Power. There's name changes, okay? But basically 44% ships to Houston, 40% of the power goes to San Antonio, 16% goes to Austin. How about any other nuclear power plants in the state of Texas generating electricity? Yes, there are. Just like there's 2 reactors at one site near Bay City, there's 2 reactors at one site near Glen Rose. Anybody from this area? Glen Rose, Granbury? Everybody's from San Antonio? Well, anyway, here's Fort Worth. Here's Dallas. Anybody from Fort Worth, Dallas? Anybody driven through there? Flew over it? Know where it's at on a state of Texas map? So they pump a lot of energy up there. There's 2 reactors at that site as well. They're about the same size, 1250 megawatt electric. I think in the relicensing and applications they boosted over years, they boosted their electric power output. They were extra conservative in the design of the original reactors. They can produce more, right? All right, how many reactors are there then in the state of Texas? 4 reactors at 2 sites. How many reactors are there throughout the United States making electricity? Not research reactors, but making electricity. About a little over 100, about 104 licensed operating reactors. So if I get another quiz up and running, it'll look like this. It'll say how many nuclear power plants are currently generating electricity in the state of Texas. I pause and I have an opportunity for row number 6. Only row number 6. Who's row number 6? Raise your hand. Yep. You guys. Okay. A, B, C, D, or E? A? I think you're all correct. Congratulations. Aircraft. You know, Standard Aero is operating in the city of San Antonio down at Kelley USA. And they repair and overhaul the T56 turboprop engine, and there's a lot of them out there. That T56, they are basically older engine designs. They are right here. There's 4 of them on a C-130. Okay, so they refurbish those engines down there, and it's old aircraft, but hey, it's still being serviced. The C-130 military aircraft, hey, row 7, uses what type of engine for propulsion? Turbojet, turbofan, turboprop, turbo screw, or turbo Mach? Only those in 7. Oh, let's go, yeah, from you down. We'll go C, B, C, B, C, C. Let's go back and look. What one is it? Turboprop. So it's a turbo prop. Very good. Thank you for humiliating yourself in front of your friends. Air conditioning systems. Oh, man, I left out of here. There's an aircraft company, Sino Swearingen, was founded in the city of San Antonio. It operated for many years out by the airport. They had been bought out by some investors from Taiwan, who then sold to some Arab Emirates country investors, who then were bought out recently by a company out of Utah. You could look them up. They make a little cute little business class jet and aircraft. It has little turbofan engines on there. I think I skipped it. I think I left it out of here. And it was founded in San Antonio. Operates the headquarters still by the airport. Still by the airport. They changed the name. For many years it was Sino Swearingen, but it's another name now, and I forgot it. Sorry about that. I was going to update these slides. What? Cyberjet. Thank you very much. Do you work there? Used to. Okay. Well, I know they went through some transitions. And there was a student that was in this class many years ago, over 10 years ago. I can't remember his name. But he wasn't doing so well, and so he took off and he went and he worked for that company. And then he came back a couple of years later, and he was all suited up he was a pilot. Wow. And so he was working for this aircraft. He said, well, they would take it out to West Texas and fly maneuvers, and they did all sorts of stuff. And when that happened, there was an opening. So he was promoted up, and so he was then flying that as not the main pilot of the test, but the co-pilot.
Yeah, he was doing a stall test.
Stall test. Oh, you even know that one, huh? Do you remember what year that was?
2002 or 2003.
I'm going to update my slides based on your information. Thank you. You're going to come by and feed me more. But then he did very well. He told me all about how successful he was. He finished his BSME, and now this student started an independent company somewhere, servicing the aircraft industry in San Antonio. Very specialty niche. I forget what it is. But there's a lot going on. Also now in air conditioning, a lot of students will graduate from here and get into the air conditioning field. Either they'll work for Trane, who has a big manufacturing facility somewhere near Tyler. Anybody know where Tyler is? Yeah, East Texas. And a student that was at UTSA wanted desperately to go back to his hometown in Tyler, and that's where he's working now as a compressor engineer. Okay? Works on compressors, designing the new stages of compressors and the manufacturing facility up there. Also, there's a company called Goodman. They really don't advertise, but they have a large share of the residential HVAC market. They're located in what city in Texas? Not San Antonio. Houston. Yeah, headquartered in Houston. It's big. You got a shirt on. Stand up, show them the shirt. See? It's a company. This is a big company. I don't know what percent of the market share does Goodman have of the residential? 30-some. They are a big company, and they have great warranty. They have great products, and they're right in Houston, in the state of Texas. All right. Refrigerators. Nobody that I know of makes refrigerators, but the same principles behind refrigerators, as well as air conditioners. Anybody heard of Friedrich? Yeah. As a window unit, they dominate the window units business. That's what it's room air conditioners or window units, whatever you want to call them. It was founded in the city of San Antonio a long time ago. They didn't start making air conditioners then, but it's been a continuous company since then. And they were out in the Pan American Expressway up until about 5 years ago. And then they moved their headquarters to this location, which is right by 281, 410. What is this? The airport. They're right by the airport, okay? They have employed some UTSA grads, mechanical engineers. I don't think they employ as many because they moved in 2006 all of their manufacturing out of the east side of San Antonio, making all these window units. They moved them to, guess where with NAFTA? All the production to Monterrey, Mexico. So all of their state-of-the-art production. But it's very unique. There's only one of them. They're the sole manufacturer of window air conditioners or room air conditioners in North America. That's it. It's a tough, tough business. And they're fighting and competing against a lot of international competition from overseas. But they have a good product, and I hope that they stay in business for a long time. And I hope they hire more engineers and help them with their business. This is a big chiller. You almost have to see one of these up front and personal, walk around it to understand. It has 2 pipes coming in and 2 pipes coming out. You have water that's going up to, let's say, a cooling tower and back from a cooling tower, and then you have water that's actually being chilled by this chiller, and it then goes out very cool and it goes to a building like this building on campus. This is a picture of a chiller on campus right here. I took that picture. And it provides air conditioning to big buildings. So on a campus, you have a lot of chillers. Big buildings, you have a lot of chillers. You don't have window units, you don't have the Goodman or packaged units or anything like that. What you have is something like this. Now that's made by York, and there's a big manufacturing facility in the southeast side of San Antonio. They were bought out by Johnson Controls. So it's now Johnson Controls as you drive by the building, but it's on the southeast side of San Antonio. Anybody know where that's at? Which you're going to what's little WW White? As you're going to what city out there? Is that China Grove?
I think so.
Is it going to China Grove?
Yeah.
It's somewhere out in that vicinity. And you can get a tour. And I have toured that plant, and that they make those chillers there. And we have a number of them on UTSA campus. Well, hopefully you're all psyched up now. Are you all psyched up? Study and learn. And you apply this stuff. You have a lot of careers that are opening up because of the foundation laid in thermodynamics. Well, let's talk about systems, then we go through a whole bunch of topics. System is defined as a quantity of matter or a region in space, either one. You choose the system to help you do an analysis, right? But you have to be clear of what's the system, and then what's not the system is called the surroundings, and you designate the difference by a dashed line called the boundary. It's all pretty simple. Free body diagrams, the basics of statics and dynamics. True? All right. I'm going to pause right now, and I'm going to tell you, you probably don't need to take many notes. Just stay alert, okay? Because I got a lot of slides to go through, and I'm looking at 111 of them. And a lot of them are simple like this. So get the concept, and then if you want, I think I'm going to try and post this up if the recording's good to YouTube. So we talk about the boundary as what separates the system from the surroundings. Be very clear. This is the boundary. Sometimes students have a poor free body diagram, hence they can't solve the problem in statics or dynamics. Same in thermodynamics. If you don't have a clear concept of your system clearly defined, then you botch it. So the system would here is shown to be the gas that's trapped in a piston cylinder apparatus. You can have a closed system, meaning that you can have heat transfer into the system, you can have work transfer out of the system, but the mass is constant. There's no mass transfer across the boundary of a closed system. The energy can change, go up or down of a closed system. The size can go larger or smaller of a closed system, but not the mass. No mass across the boundary. Here is an example. That piston cylinder apparatus, the mass that's trapped in there is constant, even though it may expand, compress, heat up, be cooled down with heat transfers, etc. There's a work transfer associated with pushing back that piston. The gas is the system. It pushes back the piston. It does work on the piston. All right? Your boundary can be movable for a closed system. Here's your state 1. Here's state 2 of the system. It's an ideal gas. It started at 3 cubic meters. It ended at 4 cubic meters. How is that possible? Well, it's constant pressure because the weight of the piston doesn't change on top that seals it. But your flame is heating it up. And it goes from 300 Kelvin to 400 Kelvin. And it will mathematically work out such that the volume goes from 3 cubic meters to 4 cubic meters. Okay? Because of heating up. So that's an example of the system having a movable boundary. The boundary pushed up that piston. Why do we spend a lot of time on pistons and cylinders? Internal combustion engines. I think it's one of the top 10 inventions of all time, right? The Industrial Revolution, internal combustion engine. We use them all over. And you own them. You love them. A lot of mechanical engineering majors want to be mechanical engineers because of the internal combustion engine. and automobiles and playing in the garages of stuff like that. So that's why we study those here. And notice that that reciprocating back and forth motion is translated or transformed into a rotary motion because of the crankshaft. And as an aspiring mechanical engineer, I know we don't study crankshafts in this class, but you might want to touch a piston in once in your life and play with a crankshaft and do things like that. All right? Otherwise, it's just very abstract and unapplied. But what we study is very applied. It's very applied. Control volumes are open systems, so they can have mass coming in, mass coming out. So here is a nozzle, and it has a dashed line indicating this is my region of focus. And now, we often, our control volumes are fixed regions in space, and we have flow in and flow out. So that's an open system. We use control volume analysis. Here, in this case, it's probably not that the mass inside the control volume changes with time, but it could. It could change with time in a control volume. What's an isolated system? Well, an isolated system has no mass transfer and no heat transfer and no work transfer, no energy transfer at all with its surroundings. So it's isolated from the surrounding. So that's what this hashed line is supposed to indicate. It's like insulated with no work and no heat. It's isolated from the surroundings. Now, one of the tricks with these isolated systems is you can have where it's hot initially on one side, cold initially on the other side, and then you allow the system to come to equilibrium with itself, by itself, without any interaction with the surroundings. So you can have difficult problems to solve when you have an isolated system, but that's how you would do it, right? You would start with the system, maybe you say, I have warm water with ice cubes in it, and it's isolated from the surroundings. Find the final temperature after it comes to thermal equilibrium, meaning the ice cubes have melted in the warm water. So we're done with systems. Let's talk about properties. First of all, the continuum assumption. We know that matter is made up mostly of void, emptiness. And then you have little molecules floating around. That's the continuum assumption. So very small particles consume a very small part of the space, and yet there's so many of them, and they're interacting that we just consider it as a smooth continuum approximation. And then if you have 1 cubic millimeter, so somebody wants to say, how big is a cubic millimeter? Millimeter by millimeter by millimeter. That's not very big, true? There are an astounding number of molecules at this room temperature and pressure. That's a lot of molecules. I wish I had $1 for every one of those. I wish I had a penny. Give me 1/10 of a penny for every one of those molecules. I'll be happy, right? That's a lot of molecules. Mass, volume, temperature, pressure, these are all properties, okay? And if you know the mass of the system and the temperature, the pressure, you know the system, you know the condition or the state of the system. That's how we know a system. We describe it by knowing values for properties. Now, a property is a property if and only if its change in between two states is independent of the process. I say, today it's some temperature out. I don't know, let's say it's 90 degrees F is the high today. Yesterday the high was 85 degrees F. That change in the property is 5 degrees F. True? Does it matter if it got down to 60 degrees at night, or 45 degrees at night, or 30 degrees last night? Does it really matter if I just want to know the difference between the temperature, the hot of the day, between yesterday and today? It really doesn't matter what happened during the night. That's why it's a property. Okay? You just have to really work with this concept. That may be so abstract to you it's not applicable, but somebody says, I have a piston, or give me another example. There's state 1, and this volume is, 2 liters. This volume is 2 liters. This is the same system at a different time, state 2. Okay, state 2. What's the volume? It's at 3 liters. What's the change in volume? 1 liter. Does it really matter if it went from 2 to 8 back to 3? Or 2 directly to 3 without ever going above 3? You know, it just matters the end state. It's a property. It's a good property. Intensive and extensive. These are definitions of properties. It describes a type of property. If it's intensive, it does not depend on the size or extent or mass of the system. And if it's extensive, it does depend on the size or the extent of the system. The test is you start with something and you cut it in half. So let's do this. If I have a system and I think, is mass extensive or intensive? Think about a 4 kilogram system. I cut it perfectly in half. I now ask the question, what is the property mass for the left half of the system? What do you say? 2 kilograms, true? It's 2 kilograms, hence it's extensive. How about the volume? It started to be 8 liters. How big is this side? It's 4 liters. It's extensive. What about density? It started to be water. Everywhere it's 1,000 kilograms per meter cubed. If I cut it in half, I ask, what's the density of the left side? Is it 1,000 or 500? It's 1,000. It's intensive. How about temperature? It starts out 25 degrees. I cut it in half. Is it now 12.5 degrees? No. That's intensive. How about the weight? Extensive. Pressure? Intensive. You're right. So the test is you just take it and cut it in half and then ask, did that property, temperature, get cut in half? Did the pressure get cut in half? Well, the mass did and the volume definitely did. So those are extensive. This is intensive. Make sense? Specific properties. Did you know that you could take volume and divide it by mass? We just said volume's extensive. Mass, extensive. I take the ratio of 2 extensive properties, I get specific volume, intensive. So this one's intensive. Okay, so often what you do is you just normalize the property per unit mass. You call it not just volume, call it specific volume, and that's an intensive property. Or if I have the total energy and I divide it by the mass, the total mass, then I have an intensive property known as specific energy. The key, divide by mass. Then you pick up the term specific. States. We talked about this already, but you describe the state of the system by knowing the values for the properties. And what we're going to find is the state principle says for a simple compressible substance, pure substance, all I need is 2 independent intensive properties. I fix the state, I can get all the other intensive properties of interest. So we'll get to that in the next chapter, but the state is characterized by the values of properties, especially intensive properties. Equilibrium. These are concepts, mechanical equilibrium, thermal equilibrium. These are less used, phase and chemical equilibrium, but mechanical is the balance of force. If things are balanced in force, there's no change to the system like acceleration because of an imbalance of forces. It's a mechanical equilibrium. So when I have a piston and it has some weight on it and it has some pressure below, this can become in equilibrium. Some of the force is equal to 0. It's not accelerating. Hence, I have mechanical equilibrium. And I can get a relationship between the total weight of the piston. You'll also have pressure acting on top, pushing down, right? So the delta P from this side to that side is equal to the weight per unit area. That's from a force balance, mechanical equilibrium. Temperature. If I have something that is in thermal equilibrium, there's no temperature imbalance. They're at the same temperature. phase, what you could have is you could have a vapor and you could have a liquid. And there's going to be an interface in between them. But there will always be some liquid turning into vapor and some vapor turning into liquid on a molecular level. There'll be some exchange. But when there's a net exchange that's balanced, you're in equilibrium, even though you have some liquid, some vapor. And in chemical, we'll get to that in Thermo 2 at the end of the semester on Thermo 2, but basically you have a chemical reaction and you have products, reactants, but you can have a balance where you have some products and some reactants all in equilibrium at the end of the reaction. You've seen it in chemistry. Process. Well, we like to put these, first of all, on a property diagram. X-axis, some property, just call it A. Could be temperature, could be volume, could be pressure, could be whatever. Another property on the Y-axis. You find your initial state, maybe right there, state 1. And then the system can undergo a process, a change, a sequence of states until it gets to the final state, state 2. We use these all the time, property diagrams. Processes sketched on a property diagram. Here, let's say this is a volume diagram right here. Well, we'll move to that in the next slide. But the process is a sequence of states, okay? Sequence of states along. Here's the next slide. Let's take and start at state 1 and go to state 2 in this direction. What we'll do is on the x-axis, we'll plot pressure. On the y-axis, volume, and then on the y-axis, pressure. True? Conceptually, line up a piston cylinder directly underneath, and the system defined as the gas trapped inside the piston cylinder. If the piston's way over here, what is the volume? 0. And the pressure? Probably infinite. But we start with the system right here at state 1 where it's lined up. And so the volume is the length here times the cross-sectional area gives you the volume. True? As you compress the system that goes to the final state 2, it's lined up. The volume has decreased. The pressure has increased. And that would be an example of a system where you're compressing it. Okay? We study this ad nauseum, which means till you're sick and tired of it. And you master it, and then you pass exams and move on, right? All right. Let's find which row have I not asked questions of? Which row did I not allow participation? That row? There's 4 people in it. Row 7 or row 8? Row 8? All right, sorry you guys, you get to answer all 3 of these. There's only 1, 2, 3, 4. So I want you to interpret what is happening in this illustration. Describe what's happening in that illustration to me.
Constant pressure.
Constant pressure? Okay. Anything else that you can say? And the volume decreases, right? So constant pressure, compression. So you're off the hook and you're off the hook. There's 2 quiet ones, all right? So the 2 quiet ones, describe that process for me.
Pressure increases, volume is constant.
Constant volume, pressure increasing. True? All right. And the row behind, there's 4 right here. Yeah. So the pressure is decreasing, the volume's increasing. All right. And you'll get very good at reading these diagrams and interpreting them. Okay. So what about this process about compressing? It started here, went to there. Let's say you're compressing, and before you get to the final state, you stop right there. If it's always a quasi-equilibrium process, that means wherever you stop, if you did stop, it would just end right there. meaning that it's just a little out of balance to make a process go, but it's so infinitesimally small out of balance that it would be in balance if you stop the process. Okay, it would be in equilibrium if you stop the process. Think about it this way. If I'm compressing and I compress it slowly, what's the difference in the pressure at the face of the piston versus way over here? The same. But if I compress it so fast, I'm approaching the speed of sound as I compress it, there would be a much higher pressure right on the face and a lower pressure over here. That would be not a quasi-equilibrium compression. Because if I stopped immediately, there would be this acoustic equalizing of the pressure. But this quasi-equilibrium process is really a good concept of you're infinitesimally close to or far away from the current equilibrium state. If you stopped right then, it would just stay right there. Cycle. We understand one process, start here, go to there. You could have it followed by another process, start here, go to there. Followed by another process, start here, go to there. Followed by a last process, start here, and you end up at the place you started. Hence, you operate in a cycle. You're going in a loop. The initial state of a cycle is the same as the final state. Okay? So as you sketch it, you can see here, this is expansion. This is very rapid expansion. This is compression and very rapid compression of an ideal gas. I'm going to pause just for a minute. All right, you ready to go again? So, ready to go? So we did, everybody get a copy of the syllabi? Some people ask me questions. Yes, do all of these quizzes that are on Blackboard. And there'll be some modest incentive. Maybe like if you get all of them perfectly right, 5 points on the first exam. Extra credit, okay? But it's not going to be tremendous, really. It's just helping you learn the material. And give me your feedback if you think that those little online quizzes are helpful or not later, okay? I know they're a little buggy and quirky. But let's continue on. So let's move on. So a lot of processes can have some of the properties constant during the process. We just talked about, hey, I described that process as constant volume, constant pressure. So one of those would be isothermal, temperature's constant. Isobaric, what's that? Pressure's constant. These are used interchangeably, isochoric or isometric, same. What would that be, isometric or isochoric? Take a guess. Constant volume. Constant volume. So a lot of times you'll see that iso, that's a key. Oh, iso something is constant temperature. You can have a steady flow process. What that means is you're coming in and you're going out. The energy within this control volume and the mass within the control volume is constant with respect to time. It's steady flow. It may flow in hot, and it may go out cool or cold, okay? But it's steady, okay? If that would happen, there'd be a constant removal of heat, constant rate of heat transfer out of the system to make it work where you're coming in hot, going out cold. Here's an example of one where you could have heat transfer in. You could have a shaft work or power coming in. So this is with unit time, work per unit time. So it's a power. That paddle wheel is going to make it want to get hot by beating the fluid. The heat transfer is adding heat to it. So the cool fluid would come in cool and go out hot, but it could be very steady flow. State postulate. Well, this is what I mentioned a little bit earlier. You just take it for granted. Here it is. The state of a simple compressible system is completely identified or specified if you know two, not three, but just two. They have to be independent intensive properties. Hence, if you know that, then you can get other values, look them up in tables or calculate them in different ways. This is called the state postulate. Okay? It's a little abstract, but we use it often. It has to be a simple, compressible system. And there's just two independent intensive properties. All right. Now, if you have electrical, magnetic, gravitational, motion, surface tension effects, then it gets a little beyond, and maybe you need three independent intensive properties or more properties. But if we're looking at steam, and I want to know the internal energy is a function of temperature and pressure for superheated steam, it works. Steam's not affected by the electrical, magnetic, and we're just talking about its property value. We would separate out its kinetic energy and its potential energy into a different part of the energy balance. So whenever you have electrical, magnetic, or you can't separate out the gravitational, or you have surface tension, you have to not think that you can apply the state postulate, but you may have a more complicated fluid substance to deal with. Independent properties. Well, sometimes temperature and pressure are independent. Sometimes temperature and pressure are not independent. Did we already agree that temperature and pressure are intensive properties? They are. So we would like them to be independent. Then I can get other properties. But often, or sometimes, they're not independent. If it's superheated, they're independent. So if I can look up the value of different properties for steam at this temperature and pressure, but if it's at this same temperature, 280 degrees C, and if it's at a particular pressure, the saturation pressure at that temperature, which happens to be around 6,412 kilopascal, then I can have a two-phase mixture, some shaded a little darker. What would that indicate to your mind? A little lighter. What would that indicate to your mind? Some of it's vapor, some of it's liquid. The liquid in the presence of gravity would collect in the bottom. That's why we put the liquid in the bottom. And so it's a two-phase mixture of steam. It's all water, H2O, but some is in the liquid state, some is in the vapor state. Temperature and pressure are not independent. For it to coexist in thermal and mechanical equilibrium, that pressure can't be 6411 kilopascal or 6413 kilopascal. It has to be precisely the saturation pressure at that temperature. Okay? All right. Notice if it's 4,000 kilopascal in that temperature, it's superheated. It's superheated steam. It's not two-phase steam. Okay. More on this later. Units. We have two big systems of units, SI or metric. SI is the official name. Metric used to be the official name. They changed it to SI. Metric still used. It means the same, right? You go buy wrenches. Oh, give me the metric wrench, or give me the SAE, which is Society of Automotive Engineers, SAE wrench. That just means they're in 1/2 inch and 9/16 and 3/4 inch for your wrenches. But the other system is in the United States, still the customary system used in the United States. We could call it the British system, the English system. They moved on to the SI long ago. Let's let them go. It's only used in the United States. Let's just call it the United States customary system of units. So you need to be in the United States still bilingual when it comes to units. Now, one of the things is it's like the Great Wall of China. If you're given a problem that are in SI, you're on this side of the wall. And the wall is made to keep the people that are on one side on that side, and the other people on that side on the other side. So think of, if you're given a problem in foot-pounds and BTUs, stay in foot-pounds and BTUs and solve the problem. And if you're given a foot in the units of meters and kilojoules, and that, stay in the SI. All right. Why do we even discuss or teach the U.S. customary system? Well, when I was a student, They just said everything's SI and going to be SI, so we don't even put any units other than SI in the textbooks. And then when you graduate, guess what the old senior technicians like to do to the new engineer? Make them look like a fool. That's what they like to do. You can't be so illiterate about what's going on in the United States, you know, if you're going to probably work here. But look, it's what is still in the customary use. When will the U.S. stop using inches and pounds and feet and miles and gallons? Well, in a lot of industries, it's already gone. You buy a new automobile since about, I forget when, but it's been a number of years, 10 or 15, 20 years. There is no 9/16 inch needed. There's no 5/8. It's all metric. You mean Ford and Chrysler? Yep. Who's the SAE mechanic? Nobody? Nobody's a mechanic in this room? Been certified SAE mechanic? Anyway. Now, the aircraft industry is very heavy. If you go to Japan and you work on aircraft, guess what? It's all SAE. And the HVAC industry is very heavy SAE. So there's some entrenched industries that's just hard to change. If you go buy a house, the salesman's going to say, oh, we have a 2,000 square foot home. It's going to be hard for that salesman. Oh, we got a so many square meter home. Right? It just, you buy a 2x4 board. What do they, if you're from a country where it's metric, what is the standard construction, stick-built home? What is the wall size? What do you build? What are they? You don't call it 2x4, what do you call it? Instead of an 8-foot 2x4, what do you call it? I don't know. But you should know, right? Right? All our sodas are already in liters anyway, right? We still have gallons for milk, but a lot of stuff has already gone over. So why doesn't the president just pass a law? Why doesn't Congress just, they did. And when I was about your age, we had all these signs like this, 35 mph or 60 kph. They were all over. They were confusing. People drive 60. Ooh, hey, I thought it was... And the speedometers had all of it, but now I think a lot of them are back to just forget it. Push a button if you want it in this, or you push a button if you want it in that. But anyway, way back in '75, there was a big push, move America toward a metric, and it passed, and there's been many congressional and presidential and all sorts of directives and laws, and even in ivory tower of academia, we just don't move it. What moves? Commerce. Business. So international trade, that's what's moving it and will continue to move it, right? And that's what did move it all over the world. People need to work together. So here you go. If it's been a little bit of time, you have the meter kilogram second MKS or CGS, centimeter gram second. This is the standard SI. That is the SI, MKS. You could talk about foot-pound second or inch-pound second. This is typically foot-pound second in the United States. But you'll see the little acronym IPS. What's that? Inch-pound second. So how many fundamental dimensions are there used to describe properties, all and every property, throughout science and engineering? 7 fundamental building blocks. What are they? Here they are. Length, mass, time, temperature, amount, electric current, and luminous intensity. This is what we call the dimension. This is the associated unit in SI and the abbreviation for that unit, okay? So I will sometimes say unit when it should probably be dimension, or I'll say dimension when I'm talking about unit, but really there's a difference between the dimension, length, and then a particular unit in SI for that. All right. Any surprises on this list? No? A lot of people would have said for electrical engineers, the base unit, the fundamental unit should be the coulomb, not the ampere. Because an ampere is a coulomb per second. That's the way I learned it. But you can try to debate the electrical faculty and get them to explain why the ampere is more fundamental than the Coulomb. I don't know. All right? But it is the ampere. And so that's the little discussion right here. And Mr. Ampere and Mr. Coulomb. I guess one was more popular. I think it's more, which one can be more easily replicated or measured throughout the world. Secondary, here you go, a bunch of secondary. So you have area is length times length, SI, meter squared. Density, mass divided by length times length times length, kilogram per cubic meter, etc. Okay? Make sure you know your prefixes and multipliers. So tera is becoming even more popular with computers that have terabytes of storage, right? Used to be kilobytes and megabytes and gigabytes, and then it went all the way up. But centi, these are the most popular. Lowercase k's, big M's versus lowercase m's. Micro, it didn't work, did it? Micro. The typeset didn't come across for micron. What are the basic principles used? 3. Mass is conserved, energy is conserved, and then energy is always degraded. That's basically it. The last one we'll get to, we'll talk about entropy, and we'll quantify the second law, which is one way of describing a one-way sign in a street. You go downtown San Antonio, right? You're driving, you see like only this way, you can only drive that way, right? The first time you drive, there you go, you're on the wrong way. There's a lot of police officers down there, stop and prevent. Well, there's some laws in physics that prevent certain things from happening, and there's doesn't need a police officer to prevent it, it just won't happen. So that's known as the second law of thermodynamics. It's one-way energy limits on the transformation. But otherwise, mass is conserved, energy is conserved. The second law, we could talk a little bit. The conversion of electrical or mechanical energy into thermal is very easy. You can walk into Walmart. You could say, I'm cold, it's the winter time. I'd like to plug something into the wall and get some heat out of it. I'll plug it in, supply electric energy to it, and I'd like some heat out. Trivial, trivial, trivial. So you go into Walmart the next day, I am so tired of paying the city public service electric bill, and I'd like to sell them electricity. So what I want to do is I want to get a box in Walmart where I can feed it some wood. I've got a lot of wood on my property, and I'm going to burn it. I'm going to burn that wood and make it hot inside the box, make electricity, and that'll be renewable energy, and I'll sell it back to CPS. See if Walmart can sell you one of them. They'll sell you one of the easy ones, electric resistive heater, but not the other one. That's where mechanical engineers earn a lot of their pay, in the business of doing the hard energy transfer, burning something to turn something. That's hard. So a joule is a unit of energy. Joule is a Newton times a meter, or a kilojoule. Don't forget the basics, true? Energy BTU. What is a BTU? Well, it's a British thermal unit. We still talk about it. If you go in and you buy some window air conditioner, they're going to rate it by BTUs per hour. And they'll just say it's a 8,000 BTU. Well, you forgot the hour. Do you want to buy it or not? You know? That's what they're going to say. Do you want to buy my window unit or not? It's 8,000 BTU, 10,000, whatever it is. So it's an amount of energy required, 1 pound to go up by 1 degree F. 1 pound of water goes up by 1 degree F. There's a bunch of energy conversion factors that are available. I don't know if all of these are available on your equation sheet. Some of them are. Look at your equation sheet, useful in exams. This is just out of the textbook showing that 1 BTU of energy is about burning 1 wood match. Pretty small amount, right? Also, if you want to get a sense of what's 1 pound of water, there's a lot of drinks that are around here. There's probably a water bottle. If it's a typical 500 milliliter water bottle, so half a kilo, a little over 1 pound. So you can just pick it up and sense, okay, that's 1 pound, right? So you get a good sense of a BTU as well as a pound. Density, specific volume. A lot of people have seen mass density before. It's just how many kilograms per cubic meter, true? So it's mass divided by volume. What happens if I reciprocate that? 1 over mass density, that's volume per unit mass. Well, would that ever be useful? Well, we use it a lot in thermodynamics. It's called the specific volume. And I know that it seems trivial, but if you have one property, you want a new property, just take the old property, reciprocate it, give it a new name. That's what we did. Okay? So specific volume is a new property. How about specific weight? Gamma is equal to rho g. What are the units on this? Well, it's how much weight per unit volume. How many newtons per cubic meter. If I was working in the United States customary system, what is my unit of weight? Pound force. What is my unit of volume? Cubic foot. Pound force, cubic foot. For weight, per unit volume. So specific weight. Molar values. If you see an over bar on a symbol, what does that mean? That means it's not per unit mass, but it's per unit mole. So here is without the over bar. Isn't that meters cubed per kilogram specific volume? This one, oh, it's meters cubed per kilomole. How did you make that transformation going from per unit mass to per unit amount or mole or kilomole? Multiplied by big M. All right, what is big M? Molar mass. It's the molar mass. Guess what units big M has to have? Kilograms per kilomole in order to get the answer that you want. So big M is molar mass, kilograms per kilomole. This bar, molar volume, meters cubed per kilomole, we don't really make much of foot cubed per pound mole, but that is the other unit. Okay. Here's just a number. The molar volume of an ideal gas at standard temperature and pressure is 22.4 liters. So if I have 1 mole of an ideal gas at standard temperature pressure, it occupies 22.4 liters. Anybody heard that number before? Yeah, a couple, right. I think that's in high school chemistry. There's a couple numbers that get ingrained in your head. So there's that molar mass. Sometimes they'll also call it the molecular weight or molar weight. Well, I know that weight's not equal to mass, so which one's correct? Guess what? It's used out there in terms. So somebody may, use the term molecular weight, and it's the molar mass. So you might want to just call it the molar mass. It has the same units, kilograms per kilomole. Or somebody says, I thought it was grams per mole. Same, that's the same, isn't it? The kilos just went away, or put the kilos in there, right? All right. So diatomic oxygen, O2, has a molar mass of 32 kilograms per kilomole. So if I have 1 kilomole of diatomic oxygen, then I have 32 kilograms of that diatomic oxygen. You can jump back and forth between the mass description and amount using the molar mass. So do you remember Avogadro's number? 6.022 times 10 to the 23rd. What is that? That's the number of particles per a mole. So if you want to count things that have lots of particles in them, you may want to use the mole, right? So if that's how many particles are in a mole, how many particles are in a kilomole? Is it 6.022 times 10 to the 20 or times 10 to the 26 or 10 to the 23rd? So if this is Avogadro's number, what is Avogadro's number equal to 6.022 times 10 to the 23rd per kilomole, particles per kilomole? Or what? What is this exponent right here? If I want to talk about kilomoles instead of moles. 20? Okay, we're going to vote 20, 23rd, or 23, or 26, or other. Or other, right? Everybody patiently in your own mind, sit there, come out with a number, and be ready to vote. Okay? Now, and what we'll do this very scientifically. We'll do it by row. Should we start in the back row or front row?
Go with the back.
The back row is nominated. So we'll start from this edge and go across.
6. 20.
Which one?
Other.
20? All right. 20? 23. 26. 26. Which one? 26. 26. 26. Let's see where we at. 26? All right. I'm going to let you struggle with that one. But can all three answers be right? No. Struggle with it. Zeroth law. Okay. Thermal equilibrium. There's a law called the zeroth law. You need to be exposed to it. This is it. It says if object A is in equilibrium with the thermometer C, they will be at the same temperature. If object B is in equilibrium with the same thermometer C, then they'll be at the same temperature. Hence, I can conclude that object A is at the same temperature as object B. Well, that was nice. It's the zeroth law. And I think most of us would have accepted that without a law. Temperature. Students need to spend some time on temperature. You know temperature. Everything's boring. Oh, blah, blah, blah. Yeah, but let's really get the temperature down. So freezing point in Fahrenheit, 32. Boiling point, 212 at 1 atm. There's 180 divisions, 180 degrees between the two. It's 0 degrees, 100 degrees Celsius, 100 divisions in between. So a temperature change of 1.8 degrees F is equal to a temperature change of 1 degree C. True? 1.8 or 180 degrees F temperature change is equal to 100 degrees C temperature change. Not the magnitude of temperature, but temperature change. Often we talk about temperature changes or the magnitude of the temperature. Do you agree with this? It is true. All right. So let's continue to this. We get our names after these Swedish astronomer, German physicists. They did a lot of work a long time ago. I'm glad they did it, and I can just trust it. But this Celsius, formerly centigrade, forget centigrade, it's Celsius, okay? And Fahrenheit, Kelvin, and these are absolute, these are relative scales, okay? Relative scales. You just saw how they're pegged to the boiling point and to the freezing point of water. All right, let's take a look here. Absolute zero. Is there an absolute zero temperature? Yes, it's 0 Rankine and 0 Kelvin. Well, how cold is that in degrees C? Negative 273 and negative 460 degrees F. All right. Do you think if the name is absolute zero that you can have a temperature of negative 5 Rankine? Why not? It's physically impossible. It's physically impossible. All right? They can't even get to zero. The physicists are working really hard, and they get shavingly close to zero, but they never get to zero. Maybe the lowest temperature is 10 to the minus 6 or something now. I don't know. Kelvin, all right? So let me ask you this. Can you get to a negative 475 degrees F? Have I ever seen a senior design project final presentation at UTSA where the people stand up there and show calculations where the temperature goes to some negative 1,000? Excuse me? What temperature scale are you working in? Well, yeah, it can't be Kelvin. It must be in degrees C. Can you get a negative 1,000 degrees C? No, you can't. You can't even get negative 275 degrees C. So there's a bottom limit. Now, there's not really an upper limit to temperature, but we should know about the bottom limit. It's called absolute zero. And you have to remember then what it is on your relative temperature scales. Oh, I forgot to point out the triple point of water. This is where in equilibrium you could have 3 phases of water coexisting. It's at a special pressure and a special temperature. Only one temperature, one pressure. Otherwise, it's not going to exist for water. And that temperature is 0.01 degrees C. Very close to 0 degrees C, 0.01 degrees C. The pressure, we'll worry about that later. Now, how about these other values? We already talked about boiling point, 100 degrees C, 212. We talked about freezing point, 0, 32. Talk about this D. This is absolute zero, right? What is this? Negative 40 is equal to negative 40? Very interesting. Temperature is a measure of hot and cold, right? Hotness or coldness. At some value of coldness, which is pretty cold, they have exactly the same numeric value of negative 40 in both degrees C as well as degrees F. Right? So that's a very special temperature. Notice the temperature change of 1 degree C change is equal to 1 degree Kelvin change. 1 degree F change is 1 degree R change. We already talked about 1.8 degree F change is equal to 1 degree C change. All of those are very important. You need to master temperature. I'm going to talk about this later. All right, here is that comparison of the magnitudes of the temperature scale. So the same change in temperature, the same change from cold to hot, is 1.8 F is equal to 1 degree C change. Pressure. This is very confusing. Pressure seems so simple, but there's a lot of units. Force per unit area, right? Everybody got pressure down? Force per unit area. You have gauge pressure. This is the tire pressure. Typically, you put in 30 psi. Its gauge is measured with respect to the local atmosphere. It's the atmospheric pressure right out here. We're currently at about 15 psi pressure, 14.7, right? So if it's around 15 psi atmosphere and you put 30 psi in the tire, what is the total absolute pressure of the air in the tire? 45 psi A. 45 psi A. Absolute for A. See? That's the pressure is 45 psi A if you have 30 in the tire. 30 psi G. Atmospheric pressure does change as you go up in altitude. Go up in altitude, the pressure does fall. This is millibar. Okay, so it's about 1,000 millibars atmospheric pressure. All right, I already did this one. What happens if you're a light pickup truck? You got 50 psi G in your tire. Add 15, there's your psi A. All right. Hey, I thought you spelled gauge differently on the previous slide. British spelling, English spelling, gauge, you can spell it different ways. Barometric pressure. This is the measure of how a barometer measures your barometric pressure. True? Do you know how a barometer works? What do you call this long, slender glass cylinder? True? It's like a glass tube. It's open on one end, rounded and sealed, right? Like a cup, but it's a tube, long tube. think about an experiment where I have a vat of mercury and I take that tube and I have it upside down completely in the air, right? I then move it over and I start to shove it down into the mercury. What's going to happen is you're going to get the air will stay entrapped. Maybe you'll get a little compression of the air, but this will still be air in there. True? I shove it all the way down. I still have air in there. True? I then turn it like this. What happens to the air? It bubbles out. Got it? Now, don't put your hand in liquid mercury, but we're doing a thought experiment here, okay? Now I turn it back again, upside down underneath. What's it filled with? Completely filled with mercury. Completely filled. Where did all the air go? It's out of there, right? Now I lift it up and I bring it a little bit out of the mercury. What is right in this region right there? How did the air get in there? Okay. Keep guessing. We have air and vacuum, both wrong. It's mercury. It's mercury. How about if I bring it up a little bit more? What's all in there? All mercury. I bring it up a long way, and finally, there's something that doesn't appear. The mercury only comes up so far, and there's apparently nothing in the glass above it. What's in that nothing in the glass above it? Mercury vapor, which is so low pressure at that temperature, room temperature, that it's basically a vacuum. We ignore its pressure. There's nothing pressure pushing down on it. There's no air in it. There's nothing pressing down on it. So we do a free body diagram of this standing here, true, and we can correlate, determine measure the atmospheric pressure about how high the push is up in the mercury. How high will it go? 760 millimeters. How many people can take their two hands and give me a visual image of 760 millimeters? Is it about this much? 760 millimeters? Or about that much? Yep, right? It's a meter. Somebody give me a meter. Give me about 3/4 of a meter. Right? Right? Okay. You guys want to talk in feet and inches still. There it is. One atmosphere is 760 millimeters of mercury column. They named it after this man, Torricelli. They call it a torr. So 1 millimeter of mercury column is a torr in honor of that man. And if you do great things in science, and maybe you too can get a nice statue made later. I wonder if he was able to enjoy his statue before his death. Probably not. Now, let's say that mercury is used in the barometer, but you want to use water because mercury is expensive and water is cheap. But the specific gravity of mercury is 13.6. What does that mean? It's 13.6 denser, heavier, right? So water's a lot lighter, right? So I'm thinking, I'm going to have to get a taller barometer. How tall? Well, this was let's say 30 inches. That's close enough to 760 millimeters. Multiply 30 inches by 13.6. That'll give you the height in inches of water. That comes in around 408 inches. Somebody take your hands. Can you give me 408 inches? Okay, divide by 12. That'll give me about 34 feet. Can you now take your hands and give me 34 feet? I'm 6 foot tall. Visually, put 2 on me. 2, right? Head on foot. That's 12 foot. Almost there? No, double that. Not even there. That's 24 feet. Ooh, boy. 34 feet. That's a long, tall barometer, right? If it's a water-filled barometer. So, okay, let's continue on. You can check out that there's mercury vapor, essentially low pressure up here. You do the force balance to catch that height right here, and it really is telling you the atmospheric pressure pushing down here which pushes the mercury up. Thank you for your attention. I must stop now.